In section 12.6, we're going to cherry pick the information needed to describe metallic bonding. We'll save the rest of this section for Chemistry 107. The goal of covering this material is to give you a complete picture of the differences between covalent, ionic, and metallic bonding. Let's begin. Section 9.4 explained that ionic solids are formed from the complete transfer of electrons from a metal to a nonmetal. The resulting metal cation is attracted to the metal anion, and these ions are held together by electrostatic attraction strong enough to be classified as a bond. The ionic compound formed is called a formula unit. Section 10.1 described covalent bonding, which is the sharing of electrons in a bond between two or more nonmetals to form a molecule. In section 12.6, we'll see that metallic solids have their own unique way of holding their atoms together. In ionic formula units and covalent molecules, the electron density is confined between two ions or atoms in bonds. We classify this confined electron density as being a directional bond. Think of the bond as pointing to the two ions or atoms in the bond. In contrast, solid metals have a metal cation surrounded by the appropriate number of valence electrons, which are free to move about since they are not confined to the directional bonds between two atoms. In this diagram, we can actually pair up the valence electrons to the metal cations to see that sodium would have one electron floating freely for every sodium cation, and magnesium would have two valence electrons free to roam throughout the solid for every magnesium metal nucleus. Knowing this, what would the electron C model look like for aluminum? Think carefully about the number of valence electrons to answer this question. We see that aluminum would be represented by a +3 aluminum cation and 3 electrons per cation. In a solid composed of 3 aluminum atoms, there would be 9 valence electrons roaming freely throughout the metallic solid. In summary, metals are a type of crystalline solid where the metal nuclei are held firmly in place while the valence electrons circulate freely between the nuclei. This doesn't mean the metal atoms have lost their electrons, they just hold on to them very loosely in the solid. The ability of electrons to move freely through the solid means the electrons will flow within whatever shape the metal takes. This allows metals to be hammered or bent into different shapes without breaking, malleable, or drawn into long thin wires, ductile. Finally, if you've ever made the mistake of touching a hot car that sat in the summer sun, you've realized that metals are good conductors of heat. Metals also conduct electricity, which is why copper is so valuable in making wiring. I've trimmed the parting thoughts of the authors to what is relevant for this short introduction to metallic bonding.